Hi, my name is Soledad and today I'm going to present my poster named, Effect of Crystallinity on Permeation and Quercetin Release of Biologic Chitosan, Ramon Starch Bioactive Films. The reason to do this project is due there is an emerging interest in using residues and byproducts from agricultural activities and the food industry to obtain biopolymers. One of the most used polymers for these purposes is cornstarch. However, it is also used for human consumption, so other sources have been explored, such as the one obtained from the seeds of Ramon, Brosimum alicastrum, a tree from southeastern Mexico. In general, starch can be processed with existing polymer processing technologies, and starch-based materials have excellent oxygen barrier properties. However, these materials present poor moisture barrier properties, brittleness, and a low tensile strength, limiting their applications. In his sense, starch can be blended with other natural biopolymers to form composite materials to mitigate these disadvantages and obtain additional functional properties. One of these biopolymers is chitosan from shrimp industry waste. Due to its antimicrobial properties, it can be used for producing food-grade films. It has been added to starch matrices from distinct sources, such as tapioca, corn, potato, wheat, cassava, and kudzu, developing films with improved antimicrobial, mechanical and barrier properties. In this sense, different phenolic compounds have also been incorporated into chitosan blends to obtain food packaging films with antimicrobial and antioxidant capacities to increase the shelf life of products and enhance their safety and sensory properties, while preserving food quality. In addition, polyphenols such as quercetin are added to enhance the antioxidant properties. In general, the functional properties of packaging films can vary due to the degree of crystallinity, DC, affecting the active migration rate of polyphenol and its gas permeation capacity. The methodology is first dissolving BCh powder, 2% W, in 100 ml of acetic acid solution, 1% V, at 25 C. Glycerol was added 25% with respect to the total biopolymer mass. Also, dissolving RS powder, 1% W, in deionized water at 80 C for 15 minutes. Glycerol was added 25% with respect to the total biopolymer mass. Both solutions were agitated for 10 minutes and treated in an ultrasonic bath, Bransonic 3510 RMT, Branson Ultrasonics, Company, Danbury, CT, USA, for 10 minutes. Next the solutions were placed into petri dishes, 0.3 grams per square centimeter, and dried at 50 hollow bullet C for 48 H. The obtained films were stored using a sodium bromide saturated solution at 50% relative humidity, RH, at 25 hollow bullet C for 48 H. After, blend solutions, 100 ml, were prepared with a volume ratio of BCh, RS of 4:1, BChRS80-q, and 1:4, BChRS20-q, all of which were added with quercetin at a concentration of 5 mg per milliliter in ethanol, in a proportion of 0.35% with respect to the total biopolymer concentration. Glycerol was also added to the blends at 25%. Films of BChRS80-q and BChRS20-q were prepared according to the methodology described above. Gas permeation analyses were performed at 25 C using a homemade setup according to the constant volume, variable pressure method. The membranes were cut into discs of 50 mm in diameter with thicknesses around 1 mm. CO2 and O2 gas, Praxair, Quebec, QC, Canada, was charged to the feed side at a pressure of 17 psi, and the permeate side pressure, after vacuum, was measured as a function of time. The permeability P, bar, was determined with this equation, where V is the volume of the downstream chamber, T is the absolute temperature, R is the universal gas constant, A is the membrane area, L is the membrane thickness, P1 is the feed pressure, P2 is the permeate pressure, and dP, dt, represents the slope of the permeability versus time curve. For DRX, samples were analyzed with a diffractometer Bruker D8 Advance, CUK alpha, lambda equals 1.5418 Armstrong, 40 keV and 30 milliamperes.
The diffraction pattern was determined by the occurrence of crystallinity peaks in the angular range, with a time and size step of 0.5 s and 0.02 ah, respectively. To determine polyphenol release kinetic, two different solutions of simulated feed, 50% ethanol and 95% ethanol, and water were prepared. 0.036 grams of each film was weighed and placed in amber vials in each simulated feed and water solution. Quercetin release in each of the solutions was monitored for 0, 1, 2, 4, 6, 6, 8, 9, 24, 24, 96, 120, 144, 168 and 192 hours by spectrophotometric readings by spectrophotometer, Genesis 10 UV, at a wavelength of 415 nanometers. Now, we are going to observe the results. For DRX, the crystalline peaks are showed in the table number 1, and the degree of crystallinity in the table number 2. The higher the Ramon starch content, the degree of crystallinity increased. The opposite behavior was observed for films with higher chitosan content. In the table number 3 we can observe the values permeability of dioxide of carbon and oxygen for both films. BCh and BChRS80-q films had higher carbon dioxide permeability values compared to RS and BChRS20-q. As oxygen for permeability, higher values were observed for RS and BChRS20-q compared to BCh and BChRS80-q. For BCh and BChRS80-q films, the CO2 had high values but presented low crystallinity values. An opposite behavior was observed for RS and BChRS20-q. To polyphenol release kinetic, for BChRS80 film, the simulated food with 95% ethanol presented greater penetration capacity between the polymer chains, generating the diffusion and dissolution of quercetin. For 50% ethanol, migration was lower because quercetin is an insoluble molecule in aqueous systems or systems with more water. The opposite behavior was observed for the BChRS20 film. In the end, the conclusions: films of chitosan biological chemical mixtures with Ramon starch were obtained with quercetin addition. It was observed that the films with the highest Ramon starch content presented the highest values of crystallinity as well as an oxygen barrier. The opposite behavior was observed for CO2 permeability. The highest quercetin release was observed for the BChRS80-q film in 95% ethanol solution. The authors are grateful to postdoctoral program for indigenous Mexican women in science, technology, engineering, and mathematics, of National Council of Humanities, Sciences, and Technologies, CONUS-CYT, Center for Research and Higher Studies in Social Anthropology, International Development Research Centre Canada. PRONAII 321295, Development and Implementation of Sustainable Methodologies for the Use of Algae Biomass, Fishery, and Aquaculture Waste from the Yucatan Peninsula, for its valorization as nutritional food ingredients and functional products, 2022-01 National Research and Advocacy Projects for Food Sovereignty of the CONUS-CYT. Thanks, bye.